students, welcome back. This is Torres, Elbow Bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, please send me an email so that I can help you in whatever way I can. So lucky you, you get to hear my voice for another lecture. But the best part is we will be learning about how to interpret variance and standard deviation. Yay! As a quick review, let's go over some of the things that we learned in the last chapter and in this chapter. First, we learned how measures of central tendency, like mean, median, and mode, describe how the data is alike. In the opposite way, measures of variability describe how the data is different. There are several commonly used measures of variability. We've already discussed a couple: range and interquartile range. Range is just the difference between the maximum value and the minimum value within the set of data. So in this example that I keep showing, the highest value is 6 and the lowest value is 3, so that if we take away 3 from 6, right here, 6 minus 3, we get that the range is 3. The range is described as one number. We also spent a lot of time looking at the interquartile range. The interquartile range is the difference between the upper quartile, or Q3, and the lower quartile, which is also called Q1. This difference right here, this length right here, describes the middle 50% of the data. Just like with most things in life, there are benefits and drawbacks for the IQR. First, the IQR uses the median as a central value and not the mean. Usually when people are discussing data, they often talk about the average, not usually the median. So it can be a little bit confusing. Also, the interquartile range is not sensitive to outliers. So although you know what the center typical values exist, when you just look at the interquartile range number, the calculation, you don't get a whole picture of what the data looks like. Another thing that's a benefit is that the IQR is a pretty reasonable summary of the spread of the distribution. But when you're building a box plot and creating your IQR, you're really only using 5 pieces of data for the 5-number summary and 3 pieces of data for the IQR. Again, you're not getting a really big picture of what the data is doing as a whole. As I stated earlier, the IQR does give you an idea of where the typical values exist, but only the typical values in the center 50%. So because it's not generally used, it can be difficult to communicate the IQR's meaning to most people. Just as a general audience, it can be tricky. So while the IQR uses the median as its central value, and people don't usually communicate using median as their relative term, most people use average or mean as their relative term. Variance and standard deviation does as well. Both variance and standard deviation measure how far one piece of data is out away from the mean. However, the way it's expressed is different. Variance describes how far the data is spread out for the mean in squared units, so like an area unit, and standard deviation is the measure of how far the data is spread out from the mean. So in the last video that I made about powers and roots, remember we've got the linear units that describe how wide and how long something is. And if we multiply those two together, we get the area of that square. Variance would be the area of that square, while standard deviation would be the length of the width and the height. So when we're talking about our mean and our data, we are typically describing those in terms of length, how far one piece of data is away from the mean. So using variance is difficult because we would be comparing area to length, whereas standard deviation, because it's already in linear units, we would be describing length to length. It makes it the comparison much easier when you're working with standard deviation versus variance. So let's look at this diagram again. Here I have 4 as the area of my square, okay? This side has a length of 2. And this side has a length of 2. And when I multiply those together, I'm going to get the area, which is 4. Okay, so the square root of 4 gives me the lengths. It gives me an actual length, not an area. If I multiply those lengths, those equal lengths times themselves, I will get the area that covers up the inside of this square. Gives me all of it. So when I'm looking at these lengths, this will measure a distance from here to here. But when I'm looking at an area, it covers the space. Variance describes a space in 2 dimensions. Standard deviation describes a length. Variance describes how far a data is from the mean in terms of area. Standard deviation describes how far the data is from the mean in terms of length. So while we're talking about how far something is, just in general, we tend to describe that distance in terms of length. It's very, very unusual to ever describe something about how far something is in terms of area. That's why we use standard deviation instead of variance. Now, variance and standard deviation have 2 different formulas. Variance has a population formula to calculate the population parameter, and a different formula to calculate a sample statistic. Standard deviation, same thing. They have a population formula to calculate the population parameter and a different formula to calculate the sample statistic. The purpose of having 2 different formulas for each one of these descriptive statistics, the difference for having 2 different formulas for each of these calculations, for each of these circumstances, is because they are trying to minimize error when working with a sample instead of when you're working with the entire population. Let me explain just a little bit more. Here is a population, and from this population, 5 people were taken to make a sample. If we wanted to learn about this population, the truth exists within this population. So say we wanted to know what the average age is for everybody in this circle, the circle right here. We could ask each one of these people for their age and then take the average and we would know the truth. But as we've said, most of the time you do not have access to the entire population. You could only take a small subset of that population called a sample and then run some statistics on that to see what can we infer about the population as a whole. The reason for working with 2 different formulas is that if you're lucky enough to be working with the entire population, you don't have to account for error. You can just use the population formulas to find either the population variance or the population standard deviation. However, if you are working with a sample, you have to try to adjust for error. So by changing the formula for both the variance and the standard deviation when you're working with a sample, it starts to account for that error. For this class, we really just work with sample formulas, so unless you're told differently, only work with the sample formula. We will go over how to use the various formulas in the next lecture, but I want to start to familiarize you with some of the symbols that you'll see. Remember that variance is the measure of how far the data is spread out from the mean in squared units. So if you're working with the population variance, you will be using this sign right here. This is called a sigma, and there will be a little 2 above it to represent that this is sigma squared. And the sigma is used for the population. If you're using a sample variance formula, then instead of using the sigma, you're going to use this S. It's still going to be squared because remember, we're working with squared units. So the units of variance are the square for the original units. If you're using the variance formula for a population, you're going to use the Greek letter lowercase sigma. And for the variance of a sample, you're going to use a lowercase s. Both of them would have the 2 up and to the right of the symbol showing that these are squared units. And as you see this here, you see sigma squared and also s squared. Standard deviation also uses the same idea of units. However, remember that standard deviation is the measure of how far the data is spread out for the mean, but this time in linear units. So we're still using sigma to represent the standard deviation of the population, but notice that the squared symbol is not there. Same thing is happening with the standard deviation of a sample. You're using S, but again, these are linear units, so the squared symbol is not there. Remember that the units for the standard deviation are the same as your original units. Your original units are linear units too. So what's the big idea? Today's big idea is that variance and standard deviation both describe the spread of the data relative to the mean. The variance describes the spread in terms of squared units, and the standard deviation describes the spread in terms of linear units. Depending on whether you're working with a population or a sample, you will use a slightly different formula. The purpose of having two different formulas is to adjust for errors between the true population parameter and a sample statistic. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay? This is your teacher, Torres, saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!